good. So the purpose of this talk is to share Moxtek progress in commercializing visible wavelength meta lenses using our nano imprint lithography and etching-based approach, similar to some of the capabilities that NILT already discussed. But if you have any meta-optic development projects that require a path to high-volume manufacturing, we'd be interested in discussing the opportunity. Let's see if I can advance this slide. Let me try to escape here. Can you still see the screen?
Yes, we can see your screen.
Okay. I'm not able to advance the slide right now.
No.
Oh, there we go. Okay. Apologize for that. So yeah, Moxtek was founded 39 years ago in Utah. We have about 250 employees working on X-ray technology components and also optical nanostructures. On the optics side of the company, we've been manufacturing nanostructures for 25 years, and we offer a complete high-volume manufacturing solution, including optical nanostructure design. So the Moxtek fabs, they're all located in Orem, Utah, south of Salt Lake City. We have 8 buildings with plentiful clean room space for high-volume manufacturing. So our optics products include wire grid polarizers. We've been the market leader for a couple decades, and also include pixelated versions for polarization imaging applications, as well as various polarizing beam splitters, and more recently, patterned dielectric nanostructures, including wafer scale meta optics. So we have solutions spanning wavelengths from the deep UV to the long wavelength infrared, and we have excellent durability due to all inorganic nanostructures. Moxtek capabilities are listed here. Really what sets us apart are our various nanoscale lithographic capabilities, including nano imprint lithography and also our etching capabilities. We have demonstration scale and production scale mastering processes ready for your application, so we can help you to verify and optimize a series of designs and then scale to production with a high volume master. So Moxtek meta lens designs or meta optic designs have certain manufacturing limitations, which are currently listed here. We can make both visible and near infrared meta lenses, and we offer several options, including reflective or absorptive front side and backside apertures, integrated color filters, and also protective overcoat, which I'll show here. This is an example of our etched high aspect ratio pillars. So the aspect ratios can reach up to 15:1. So these are fairly delicate, but after hard mask removal, these structures can then be overcoated to protect against handling damage as shown here. So without overcoat, even the paintbrush can damage the metal lens surface, but with overcoat, there was no damage. And the overcoat can also act as an anti-reflective layer and boost transmission significantly. So others have discussed that the metal lens could also be infilled with a low index material, but the advantage of our overcoat is it spans over the top of the pillars, maintaining the high index contrast between air and the high refractive index material, and maintaining reasonable aspect ratio requirements. So late in 2023, we installed a wafer scale metrology tool for MTF, focusing efficiency, and other meta optic measurements. And this was an early result for a small 200 micron diameter meta lens before full process optimization. And we saw that these smallest diameter meta lenses have improved MTF performance near the diffraction limit, which makes sense since chromatic aberrations scale with lens diameter. Chromatic aberrations, of course, also scale with the source or filter bandwidth on your metrology tool. And these measurements didn't even utilize a particularly narrow bandwidth, which makes the measured MTF performance all the more impressive. So this result demonstrates the promising potential for applications utilizing small diameter meta lenses. We've also created methods to measure absolute focusing efficiency using this tool, and we've demonstrated greater than 90% absolute focusing efficiency for 1 millimeter diameter 0.2 NA lenses. Larger diameter lenses have more aberrations. Despite this fact, we decided to measure a 4 millimeter diameter conventional plano-convex singlet lens from Edmund Optics and compare that to the performance of our red and green meta lenses with the same diameter and focal length. And even though our meta lenses would show better performance with an improved filter bandwidth on the metrology tool, it's important to show an apples-to-apples comparison to a traditional lens utilizing the bandwidth requirements of the end user's applications. Perhaps surprisingly, these Moxtek visible meta lenses show better MTF contrast than the simple singlet. So overall, this was a very encouraging result. Again, these reported MTF values here are maybe lower than one might expect because these are large diameter meta lenses and the source bandwidth is fairly large for this type of hyperbolic meta lens design. So 2 years ago now, we went ahead and built an iPhone meta lens assembly with one of our green meta lenses. And here's a schematic of this setup. We aren't camera designers, as Theodore mentioned. That's quite challenging. So essentially, we just slapped our meta lens on top of the iPhone camera and used it as a simple macro lens for magnification of small features. Here are color images that we captured of a foreign banknote and the cross-section of a pumpkin stem. So to our knowledge, these were the first high-quality visible meta lenses made using production scale processing and demonstrate that reasonable image quality can be achieved when using meta lenses, even with traditional RGB filtered sensor. So Moxtek's built meta lenses in a variety of different diameters, ranging from 200 microns to 10 millimeter diameter, and we have the ability to go up to 1-inch diameter. We've designed meta lenses with various operating wavelengths from the violet to the mid-wave infrared. We could do long-wave infrared as well. And we've designed them at various focal lengths shown here. Currently, it's difficult for businesses to explore the possibility of incorporating meta lenses into their optical systems because meta lenses are generally available on a custom order basis only. So to make this kind of evaluation easier, Moxtek is making visible and eventually near IR meta lenses available off the shelf for benchtop and integration testing. So these circled samples are what we're initially offering, and other options should be available later this year. So I'd like to briefly discuss some new and hopefully exciting Moxtek capabilities, including nano stacking of optical filter components at the nano or micro scale. So traditionally, when multiple optical filters are bonded together, they can become quite thick, especially when multiple substrates are involved. Utilizing our overcoat technology, we can stack various filters on a single substrate at the nano scale, including wire grid polarizers, wave plates, meta optics, color filters, and so forth. So here's a simple example where we've built a meta lens on top of a wire grid polarizer. On the right, here's another example of a multi-stack, so meta lenses on both sides with overcoat layers, color filter, and absorptive apertures, all on a single substrate built at the wafer scale. Furthermore, this was actually an off-axis imaging meta lens for eye tracking applications. In this case, the requirements were given by Moxtek, provided to ANSYS, and the meta optic design and optical modeling was completed by ANSYS. And then partnering with our NIL tool vendor Skill, we built this stack, a double-sided meta lens stack. But actually the images shown here were from a slightly different stack where all the imaging functionality was combined into one metasurface layer on a single metasurface. So we built this kind of assembly here. And on the right is the comparison between the ANSYS modeled and Moxtek measured images of an eye. So this kind of design, off-axis design, allows some added flexibility in terms of eye tracker placement. And it also gets rid of most of the zero-order leakage issues. So we hope this demonstration of a complete meta-optic design and manufacturing workflow will eventually lead to a PDK or meta-atom library for ZMAX. But if you don't want to wait for that, I would encourage you to contact PlanOpSim, who just presented, and use the visible PDK that we've already released, which we announced at Photonics West. We plan to further develop modeling capabilities of our meta optics foundry processes with PlanOpSim in the future. Finally, we also can vary different filters or stacked nanostructures or meta-optic devices on a pixel-by-pixel basis with applications in imaging polarimetry or hyperspectral imaging, for example. Please let us know if you're interested in any of these concepts or capabilities. With that, here are my conclusions and some areas for future work. I'd like to emphasize that Moxtek already has several operational fabs, and we can scale the high volume manufacturing quite simply using our foundry processes. I should also mention that we've been working recently with Synopsys on manufacturing aware near-infrared metal lens designs based on the Moxtek foundry processes, and initial results are encouraging. Again, if you have any meta-optic development projects that require a path to high-volume manufacturing, we'd be interested in discussing the opportunity. Thanks for your time, and I'd be happy to answer any questions that you might have.
Thank you. Thank you very much, Matthew, for your presentation. And any question for Matthew? I was wondering, Matthew, how do you tackle, the challenge of scaling up the production while when you want to maintain the nanoscale precision and reduce the production cost? How do you tackle these kind of challenges?
Yeah, we use basically a nano imprint lithography approach. So all the lithography is done on a master level, all the fine scale lithography, and then we can make many, hundreds, if not thousands, of stamps from an existing master, and then we can print hundreds of wafers per stamp, so you can get tens of thousands of wafers per master. We can, I think our fabs can do over 100,000 wafers per year of optical nanostructures. And with our nano imprint tool, we can probably do 30, 40,000 wafers a year. And we could, of course, get more tools. The metrology, on the other hand, we might, if we're talking about small lenses where you have thousands of lenses up per wafer, we'd probably need to get additional tools. But we're ready with all of our tool set is 200 millimeter diameter wafer fab based. So we can manufacture many tens of thousands or hundreds of thousands of wafers fairly easily with our tool set.
Okay, great.